Hi, today we're going to talk about support vector machine or SVM. Okay, before talking about the support vector machine equations, we will go through some story. First, basically we want to minimize risk, but risk is not available. We cannot calculate risk directly, so instead we have empirical risk, so we can minimize empirical risk. But there is a question. So when we minimize empirical risk, do we actually minimize risk? Okay, so there is some connection. So empirical risk plus some term can be upper bound of risk. So to make that upper bound, we introduce VC dimension. Okay, and then assuming that the data set is linearly separable, then when we maximize the margin, then that actually makes the gap between the risk and empirical risk minimized. So from this on, maximizing margin is our problem. So we have a problem formulation. And then since there are some constraints, so we're going to use a Lagrangian multiplier, a Lagrangian function. And then the problem will be transformed to the Lagrangian dual problem. And then finally, we'll see support vectors. So by this, we have a best kind of classifier when the data set is linearly separable. But what if data set is not linearly separable? Then we can have select variables or kernel tricks. Okay, and then we'll talk about some other issues. Okay, so let's talk about risk and empirical risk. Okay, so basically when we have some task, then we have a goal. So if it is translation task, then we have a blue score. Okay, so usually blue score is not differentiable. Okay, so even though this is what we want, but this is not something that we can use in machine learning. Basically, we can use this one in the reinforcement learning, but this is not differentiable, so it's not easy. Okay, so we can define a measurement of how well a model fits the data. So that's expected loss or risk. Okay, so let's assume that we have a risk in this way. Okay, but as I said, risk cannot be measured because it has expectation. Think about expectation of people's height in the world. Then we cannot actually measure all the people. This is the problem. Okay, so we cannot measure this risk. Instead, we can use empirical risk from data samples. We can actually select some kind of 1,000 people randomly, and then we can measure their height, and then we can take the average to estimate these expectations. That's empirical risk. So instead of calculating this expectation, we just get some data samples and then take average of this loss. Okay, in this case, training is actually empirical risk minimization. So we are going to minimize this empirical risk. That's all we can do. And when the number of samples increases, then the empirical risk converges to the risk. Okay, so if we increase the number of samples, then it will converges to the actual risk. But with a small number of samples, then there is some issue like overfitting. Okay. So to avoid overfitting, the model complexity can be measured and it should be kind of controlled. Okay, so what I'm saying here is that we want this, but practically we can minimize empirical risk. But here is a question. So when we minimize empirical risk, do we actually minimize risk, or how much? So to answer to that question, then we're going to introduce VC dimension first. So the VC dimension measures the model complexity of F. And it measures the largest number of examples that can be explained by F. Okay, so let's take some examples. Okay, so when we have 3 points, then no matter how these samples are classified, then the linear classifier can separate. Okay, so this is one way or another and another. So we can separate the 3 samples. But if we have 4 points in the 2-dimensional space, then the one linear classifier cannot separate if we have this kind of case. Okay, so the VC dimension of a linear classifier in two-dimensional space is 3, because this classifier can separate 3 samples no matter how they are classified. Okay, so actually the VC dimension of linear classifiers in the d-dimensional space is at least d plus 1. Okay, so if F can explain the training samples with a small capacity, that's a good thing. Okay, so we don't want to increase the model complexity if we can explain the data samples with the simple model. Okay, and with this VC dimension, we can provide some upper bound of this actual risk. Okay, so from this statistical learning theory, we can get this upper bound. With the probability of 1 minus eta, the bound is given by this one. So this is a risk, and this is empirical risk, and there is another term here. And the DVC is the VD dimension, and the N is the number of samples. And what we want is to have a tight bound, right? So when we minimize this one, then we expect that this should be minimized too. So to have a tight bound, we can increase the number of samples. Obviously, if we increase the number of samples, even though we have an n here, but there is a log, so if we increase the number of samples, then this term will be kind of minimized. So the bound will be tight. Okay, well, let's assume that the number of sample is fixed. Okay, then what can we do? So these should be small. Okay, so when n is fixed, then this one should be small to have a tight upper bound. So d should be small, but if this VD dimension is too small, which means the model is too simple, okay, then empirical risk would be too high because the model is too simple, so we cannot minimize this empirical risk. Okay, so if this one is high, then even though the upper bound is tight, but still this risk will be high. So that's not what we want. Okay, so structural risk minimization is about the balance between the model complexity and the empirical risk. So we want a simple model to classify, but at the same time we have a powerful enough model to minimize empirical risk. Okay. So before talking about the maximizing margin, let's talk about optimal separating hyperplanes first. So for nonlinear models, computing the upper bound is not tractable, so it's not easy to get the VC dimension correctly. So actually, most of the time we don't use VC dimension in our research. Okay, so we use VC dimension in this way. So to talk about the connections between the empirical risk and risk in the linear separable data case. Only in this story we use VC dimension most of the time. Okay. So to find the separating hyperplane for a linear separable data set, okay, so we assume that the data set is linearly separable. Okay. And then optimal separating hyperplane is the one with the largest margin. So look at this one. So when we have a linear separable data set, so we have red class and the blue class, and then there are so many classifiers, but this one is the best hyperplane. So this one is parallel to these two boundaries, and when we maximize these margins, then the middle line is actual optimal hyperplane. So we have to find how to maximize this margin. So when we have two lines like this, then the margin is small. So we have to control these two lines. Okay. And then we're going to talk about why this is the optimal separating hyperplane is the one with the largest margin. Okay, so a VC dimension of a separating hyperplane with the margin M is bounded by this. By these equations, maximizing the margin is actually minimizing the VC dimension. So if we maximize this margin, then it is kind of minimizing the VC dimension. Okay. So remember, in the previous upper bound, we have a risk and empirical risk plus some term. So maximizing the margin is minimizing the vice dimension, which means we minimize this term. And then on the other hand, since this is a linearly separable, so this one is 0. Empirical risk is 0. So if we have the maximum margin, then it's a linearly separable perfectly. That minimizes this empirical risk, and actually it is 0. Okay, so maximum margin also minimizes the structural risk. So it minimizes this one too. So the upper bound is smaller and smaller and tight. So we are actually minimizing the risk. We can guarantee with some probability. So when we have a large margin, then the model's capacity can be lower. So look at this image. So when the margin is small, so this one has a small margin, then we can actually move this separating hyperplane in many different ways. But if the margin is maximum, then we cannot rotate or shift this hyperplane because it is fixed here. So the capacity is lower. So remember, in this slide, we just checked that when we maximize the margin, we actually minimize risk by minimizing empirical risk. So now what we want to do is to maximize the margin. Okay, that's what we want here.